Okay, wonderful. Sorry for the delay, guys. Yeah, Doin is. Yeah,
He's gonna go. Okay, hello everyone. This is Jiaquan, the core dev coming from Automata Networks, and that's Preston, our blockchain engineer. Today we are glad to share the TE technology in today's Threshold Summit. And in this talk, we will focus on the on-chain solution to the how to build a verifiable random number to satisfy all the random number generation and which will fuse the blockchain applications like the secure key generation, the digital signatures, and fine and lottery apps like some other Web3D apps. Okay, here is the agenda for today. I will introduce why we need the TE-based Verifiable RNG and how important it is, and we'll also give you a high-level overview of how our Automata VRF works, including the hierarchy and the whole workflow. And then to meet all the requirement, we also built our own attestation layer and a DCAP attestation which happening on chain to make it works. And last but not least, we will also introduce Automata product which use our Automata VRF in our production. Yeah. So, why TE-based verifiable RNG? And before we talk about this, I will also give you a summary on the TEs. So the TE means the Trusted Execution Environment. It is a secure enclave that designed to execute the code and process data in isolation. There are some key features for these TEs. The first one is the code and data integrity, which means the running code and the data is matched with what we are expecting, and the data cannot be escaped from outside the enclave. And for the second one is the confidentiality of the execution, which means only the enclave itself can know what is happening inside this application, and even if the operator or some other attackers, they cannot observe what happened during the application, and they cannot do anything analyze and some other potential attacks for the whole execution. So, and for the last one is about the attestation, which means we need to have a mechanism to ensure the code is running as expected, and also the hardware environment is matched the TE guarantee. And we will talk more about this in the following slides. So to summary, the Automata VRF is producing the high quality entropy that is generated by the TEs and the DRAMs. So I will talk more about the details. And yeah, before we build such service, we are thinking of what's the most important things to producing randomness. There are several kinds of characteristics we need to meet. And as the previous speakers said, for generating the randomness, we need to meet the unbiased, the unpredictable, and on-chain or off-chain verifiable, and also the reliable. So I think it's quite straightforward for the users to use such randomness if we can have one service to meet all the requirements in this case. And as I mentioned, the Automata VRF is using DRAM and TE to produce such unbiased, unpredictable, verifiable, and reliable randomness. And we have to Yeah, we have two sources of the how it works. The first one is the DRAM. DRAM is one factor to calculate the random seed, which is publicly verifiable, and the randomness derived from the decentralized networks. Like it has a device set of participants, including the protocol labs or Ethereum Foundation and other participants. So all these participants will join the consensus and use the throttle BRS signing to compute the randomness for each round. So in our hierarchy, we will use the DRAM as one kind of data source to generate the random seed. And for the other side, there is the Intel SGS API, and for this API, it uses the hardware API provided by the Intel to generate another unpredictable randomness from the hardware. So in our VRF, we combine these two random sources to generate a new random seed before we put it to the random number generator. So in this case, we will have two-factor randomness source, and it makes the attackers or the operator harder to, or even extremely difficult to guess the randomness at the same time, and if it makes it harder to pre-compute all the things and simulate the same calculation inside the encave. So in this case, we will have a more secure model to generate such unbiased, predictable, and verifiable randomness. And last but not least, compare with the existing DRAM protocol, by using the TEE, we can have a better latency because it doesn't rely on the decentralized networks and the overhead of the negotiation of the randomness. So in this case, the DRAM acts as a secure budget or secure buffer to increase the whole secure level when generating randomness. And yeah, because in the TEE environment, it can achieve the instance latency when generating it can achieve to generating instance latency to generate a new randomness number. And next, I will introduce the hierarchy about the whole things and the workflow. Yeah, as I mentioned, there are two kinds of input source. One is coming from the DRAM, and the second one is coming from the Intel hardware. And inside the in-case application, when it fetch these two kinds of input, it will try to use the calculation based on this to calculate the final random seed, and then put it to the normal random number generator, and then it will generate the result periodically and submit it to the smart contract. So, but before submitting to the smart contract, we need a TE signer to sign over the current round of the randomness to ensure the calculation is matched and it is signed over by the TE itself. And in the next, to meet what I said, we will have some attestation steps to need to meet. I will work through the whole things step by step. So there is a hierarchy attestation model to meet this requirement. The first one is the signature verification for the current DRAM result, and to make it possible to verify the whole things on chain, we introduced the ZK circuit to reduce the gas cost and verify the DRAM output. And for the second one is how do you know the code running inside the enclave is match what it claim, and we introduce a reproducible build attestation to ensure the source code is matched and the binary is matched, because we need a mechanism to ensure the source code is matched with the final binary, and also we need to consider the input configuration is matched as well. So that's the second one. And for the third one is about the Intel DCAP attestation. This is attestation protocol to ensure the hardware requirement, which means by using this attestation, we can convince others that all the things is running inside Intel hardware, especially focusing on the either Intel SGS or Intel TDX. So that's the hardware attestation. And for the final one is we need to ensure all the things is running correctly. And for each round randomness output, it is signed inside the TE enclave, and we need to verify this on the smart contract. So the final one is work as a aggregated attestation for the period 3.1. Sorry.
Guys, I don't think the clicker is working.
Okay, cool.
Oh,
Yeah. So for the first one is the verifiable execution environment, and like what I said, it acts as a software attestation to ensure the source code and the binary is running as expected. So yeah, all the things will affect the execution logic is matched as expected, and we use the AWS reproducible build tool provided by the Automata networks to have such reproducible build via the AWS Natural Hypervisor. And yeah, for the second one is the hardware attestation called the Intel SGS DCAP attestation. It is an official attestation protocol produced by Intel, and it used to ensure the application or the enclave is running inside the.
just say next slide. We'll flip them back here.
Okay. Okay. Let's continue. Sorry. Back. Yeah. To make it happen, because the original DCAP attestation requires some Intel service, we also move all this logic from the off-chain or from Intel to our on-chain PCS and DCAP attestation verification contract to make it happen. We will show more details in the following slides. And next. Okay, and as I mentioned, in order to ensure the whole randomness is correct, we also need a signer inside the TE enclave to sign over all the attestation it have, and including the current round of the randomness. So inside the enclave, we use the ephemeral key generated inside the enclave and sign over all the things, which means such ephemeral key cannot be read from outside, which means even if the operator or the attackers, they cannot know this ephemeral key other than the enclave itself. It will increase the whole secure level of our execution environment. Next, please. And last but not least, as I mentioned, we need to ensure the DRAM input is matched with what the decentralized networks provided. So to make it happen, we use the ZK protocol to reduce the gas cost to verify the DRAM signature on chain. And for the whole attestation hierarchy, as you can see in the graph, the TE hardware attestation relies on the reproducible build. So there is some dependency on such attestation layer, and in order to verify them step by steps, we introduce the Automata attestation protocol to make it happen. And next, please. Oh, okay. Oh, sorry. Okay, yeah. And for the high-level workflow, to TLDR is our Automata VRF is adding the similar interface to the Chainlink VRF. And there are two kinds of major situations that you can use our VRF is you can get the latest round of randomness directly, or you can use the subscribe method to request random number and then use the callback to receive such randomness from the smart contract. And compare with Chainlinks, our VRF can deploy to any change that we are interested in, and it also has a more secure entropy and robust entropy compared with the Chainlinks. And for the following slides, I will invite my teammate Preston to introduce more about the details.
Alrighty. Okay, so in the previous few slides, Jiaquan kind of covered the different components of the VRF, of how the different attestation works. So for me, I'm going to focus more on the network side of things, specifically on how our Automata network would handle those various types of attestations. Okay, so there are three different attestation types that our network could handle. So the first one, it's called single-step optimistic attestation. So basically what that means is that for any attestation that could be verified within a single atomic transaction, that would be considered as single-step. So for an example of that would be having a signed data included into the attestation, and then you would be able to verify that signature within one single transaction. So that's what single step is. And for the next one we have here, it's multiple steps, multi-step attestation. So this attestation type, it's very similar to what Optimism is doing for fraud proofs. Essentially, the submitter of the attestation would send that attestation onto the network, and then the network would optimistically store that. And then within a certain window, then anybody could submit a challenge saying that this attestation data might not be valid, or it could be actually completely valid and nobody would challenge that. So basically, I forgot to mention that. So for anyone who submits an attestation with the multi-step, they would provide a stake for that attestation, and then a challenger could potentially say that this is not correct and then slash their stake if it's not valid. And then the last one that we have here, it's consensus-based. So for this type of attestation, how it works is that you would have the contract owner could basically designate a group of committees, and this group of committees would essentially get to decide whether all of the incoming attestation to this contract would be valid or not. So once it hits a majority, then we could basically say that this attestation, it's valid. So for the last type of attestation, for the consensus-based attestation, this is very useful for attestations that cannot be feasibly verified on chain. So for those scenarios, then you would depend on committees to as a means of verify those attestations. So for our VRF specifically, we only used single-step and consensus-based attestation types. Okay, so I'm gonna go more in depth into DCAP attestation. So, because we've been covering a lot about TEE, so DCAP is essentially a attestation primitive. So it literally stands for Data Center Attestation Primitives. That's provided by Intel. Basically, what you could do with DCAP is that for anyone that generates a quote from their Intel SGX, they could essentially have access to their a local. You could think of it as a local data center where they could store all of the essential data that's required for verifying the attestation. So we call those PCCS. Okay, so for DCAP specifically, we have worked. We have released this Automata DCAP attestation. So it's a set of smart contracts that would allow users to store collaterals with on-chain PCCS, and for verifiers that are interested in perform attestation verifications, they would be able to use this library as well. So it is a full Solidity implementation of the entire workflow. It works with Foundry, and since this is a V4 library, it will work for both Intel SGX and TDX. So this is the entire architecture that we have for our DCAP attestation architecture. So as I mentioned earlier, the way DCAP works is that people would have access to their local source of collaterals. That's what the PCCS is, but we basically took that to the next level by putting it on-chain. So we have that on-chain PCCS component over there. So another benefit of putting it on-chain is that it kind of aligns with the values that Web3 has been talking about, right? It's to basically allowing a permissionless ecosystem where everybody could contribute certain anything that's valuable, and people could consume it without restriction on access. So we have contributors that could submit collateral permissionlessly, and for people that are interested in generating the quotes would have unlimited, unrestricted access to the on-chain PCCS. And then once we have the quote generated, then the verifier will also have access to the on-chain PCCS. And since we have all of these collaterals published on-chain, that means it's also very easy for us to have a DCAP verifier contract to read those collaterals directly through our on-chain PCCS. Okay, so this is more onto DCAP verifier contracts. So for our DCAP verifier specifically, we support two types of verifications. You could either do it fully on-chain, or you could use a ZK snark verification approach. And for ZK specifically, we integrated both RISC-0 and succinct ZK code processors. So by using a ZK snark option, you could essentially reduce a lot of gas as opposed to executing all of the verification steps on chain. So for DCAP verification specifically, one of the biggest gas costs that would incur is that you have to perform a lot of P256 signature verification, which is not natively supported by the EVM. So that's why you would be more tempted to use the ZK verification. As you could see here, it reduces the gas cost quite a lot. Okay, so I've been covering a lot about the network attestation, the attestation layers on our network and DCAP. And now we're going to go into what exactly we're doing with our VRF. What exactly are we doing with VRF? So for our use cases specifically, we're using it for one of our projects called L2 Faucet. So an L2 Faucet is, so it's a faucet backed by proof of machinehood. So that's another attestation solutions that we're providing. Essentially, this allows people to request for faucets using their device authentication. So for example, I could request for a testnet token using my Face ID, for instance. Anyway, so we're using Automata VRF as a means of creating a completely random request. So for instance, if I don't have a VRF within my request, there's a possibility where people could use a known request as a replay attack. So in order to mitigate that, we introduce a component where we would include a verified number such that each request that's coming in would be unique and unpredictable. Oh, yeah, that's about it. That's all I have for use case in the moment. So this is where you could find us. We have our social links here. We have if you wanted to learn more about the things that we've been building on Automata, you could check out our docs. And if you would like to know what else we've been up to, you could go to our X. And if you have any other questions and you would like to connect with us, you could check us out on Discord as well. And that's about it. I'll open up this session for a few questions, I guess. Nope. Nope. Do we have any questions? Yes, sir.
Yeah, so you said you use a circuit to verify the other solutions.
That's correct.
How much gas does it cost, and how long does it take to prove?
So for proving time specifically, it takes about 3 minutes-ish, I believe. And then in terms of gas costs, it's within like 100, 200K gas, I believe. I might have to check that, but that's what I recall from the top of my head. Yeah. Any more? Yes, sir. Yeah.
How do you take it from the standpoint of the OEMs? Is there a way for like Lenovo and Dell and some of these other OEMs to differentiate their hardware based on your approach, or is pretty much everybody is just commodity hardware?
So I take that you're referring to the question you have with regards to Altofalsa, right? Is that what you're trying to go for? So the thing about differentiating is that, so the problem here is that when you request for a specific token, for example, let's say I'm interested in Sepulveda ETH. So what's gonna happen here is that you would use your device private key that's stored in the enclave to sign that request, and then that request gets sent on chain, and then you would verify it, right? So the problem here is that that key, it's essentially tied to your device identity. So it's not like, I mean, maybe for some certain manufacturers will allow you to generate a different key, but I guess it's much more straightforward to just have something else to kind of differentiate like the different requests instead of having to like, to determine that, oh, for this specific OEM, you have to worry that whether do they allow you to have different keys or not. I mean, it would be a lot easier if you have like a guaranteed source of entropy to differentiate those requests. Yeah. Yeah. Thank you.
Thank you very much. Yeah.